for the last part of our energy unit, we're going to talk about energy and waves. So, a wave is a repeating disturbance or movement that transfers energy through matter or space. Okay, so the important part here is matter or space. So, waves, depending on what type they are, can either move through matter, so actual physical things, or through outer space, which is a vacuum, which has really nothing in it, unlike air that actually has air particles that can move. A pebble dropping into water is an example of waves that I'm sure you've seen. And as far as waves and matter go, so waves are just transferring energy. They do not transfer matter from place to place, so it's just transferring the energy along. So if you've ever seen a boat in a lake and there's waves that come through, the waves actually bump against your boat, but they don't carry your boat along on that wave. If you ever thought about that, you don't really take that wave and keep going with the wave the whole time. So they are just taking that energy, and I can show you a video in class, but waves actually don't even carry the water along with them. They just are transferring that energy, and the water itself is just moving up and down from where it is. All right, so how do we make a wave? So this is a normal type of wave you've probably seen before, where it goes up and down like this. We're going to look at the different types of the wave, and this specifically is called a transverse wave. All right, any wave that goes through a medium, or has to use a medium or matter, is going to be a mechanical wave. Okay, so these have to have a medium or matter for the waves to travel. Okay, so it can be a solid, gas, or liquid, or any combination of them. So these mechanical waves are ones that can only travel, let's say, here on Earth. They're not going to be able to travel in outer space if there's nothing out in a vacuum. So there's some waves, such as light and radio waves, that can travel through space. Okay, and these are what we're going to call those are going to be called electromagnetic waves. But as far as mechanical waves go, there's two types. So we have the transverse and we have longitudinal. So these are just going to be classified by what they look like. So a transverse wave, this is the normal wave that you probably thought of when I started talking about them. These are where matter moves back and forth at a right angle to the way the wave travels. So if the wave is traveling this way, the rope, remember rope, if you're holding it, isn't going to move. It's just going to move up and down this way. So that's what it means by perpendicular or right angle. The rope is moving up and down this way as you're making a wave, but the wave itself is moving the energy that way. Okay, so you're giving it kinetic energy here. That energy is being transferred through the rope through a wave. Okay, and the second type is the longitudinal wave. So this is where actually the matter or the medium is moving in the same direction as the wave. So the wave is moving to the right and the matter is moving to the right, moves back and forth, so this way. We're going to try this out with slinkies in our lab, but if you squeeze a couple coils together like this is going to be called compression. And then when you let it go, that compression is going to travel, and as it travels, part of it actually becomes more loose than it was earlier, and that's called rarefaction. Okay, so wavelength for a longitudinal wave is from one rarefaction to another. All right, so those are just the more open spots. So we said wavelengths for longitudinal go from rarefaction to rarefaction. On a transverse wave, however, they go from either crest to crest, trough to trough, or right in between. So this lowest point is called the trough of a wave. So kind of like a trough that pigs eat out of. They're shaped like this, so that bottom point is the trough. This top part is called the crest. All right, and we're also going to bring in what we call amplitude of a wave. And this is going to be how high the wave is from where it started to where a crest or a trough is. So it's just the distance between here to here. So if we get a wave that has a bigger amplitude, it's going to go further away from where it started, like that. If it has a smaller amplitude, it's going to be closer to where it started than that one. Okay, so wave equation. So this is what when we talk about waves. When we're talking about it in this class, we are always going to do waves that are always going at the same speed or velocity. So waves are going to travel as long as they're moving through the same medium. So if a wave is moving through air or if a wave is moving through water, it's going to move at the same speed. What can change is the frequency and the wavelength of a wave. So a frequency, that's just how many times something passes through each second. Okay, so this would be the number of crests or troughs that pass by a point each second. So if this is our unit of time, right here, our frequency here, if we're talking about crests, there's 1, 2, 3 that pass by. And this one, there's 1, 2, 3, 4, 5 that pass by here, and 1, 2, 3, 4, 5, 6, 7, 8, 9 that go through here. So this would be a high frequency, and that one with 3 is a low frequency. All right, wavelength, remember then, is just the distance from crest to crest or trough to trough. Okay, so this one would have a longer wavelength, and that's a lambda, which looks kind of like a little dinosaur. This one, however, is going to have a very short wavelength. So if you notice, anything that has a high frequency has a short wavelength. But if you have a low frequency, you have a longer wavelength. Right? And that's how you get the same speed for the wave each time. Okay, so how do waves react? So we have something called the law of reflection. So when a wave hits an object, so like even this light wave, or if this was a water wave going through and then bouncing back off, compared to the angle that they hit the object at, so from here to here, these angles are going to be equal. Okay, so if you ever kick a soccer ball or kick something up against the wall in the gym, the angle you kick it at is going to bounce back off that wall at the same angle. So if you kick the soccer ball here, it's then going to bounce back that way every time. Okay, refraction. If you've ever seen things in pools or you've seen those funny pictures, refraction when something's in air versus water occurs. So this is going to be due to light waves in air versus in water. So if you've ever seen this before, your straw actually ends up looking bent like this because the wave speed changes. Okay, so that makes the wave bend. So if the wave was going faster here and all of a sudden it goes slower here, it's going to change the angle that you can see the light from the straw. Okay, so we talked about mechanical waves, so those are the ones that had to go through medium. The electromagnetic spectrum, those are the waves that can go through space. So anything in this entire spectrum can travel through space and through Earth. Okay, so this whole group of things over here can all travel through space. They do not need a medium. All right, so we already mentioned this, that a longer wavelength means a lower frequency. So those would be like radio waves or microwaves. A shorter wavelength means a higher frequency. So really, really short means they come through a lot. So gamma rays, PET scans, the scanners there, and then UV lights right here. Okay, the dangerous part of the electromagnetic spectrum is due to high frequency. So you have all of a sudden wave energy being hit at you like boom, 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 boom. Okay, so that's what makes things dangerous. So UV light, you've heard about, X-rays, gamma rays, you have to be careful around all those because of their high frequency. Okay, that high frequency and that amount that energy is hitting you, one right after the other, can mess up things in your cells and in parts of your body. And so this is the dangerous end of the spectrum. Okay, so this is just kind of some more examples of the electromagnetic spectrum. So if you see here, radio towers, which have a lower frequency, have a bigger wavelength, 10 to the third, so that's 1,000. Okay, that's like around, well, that one's about, 1,000 is about the size of a tall building. 10 to the 2, which is 100, is about the size of a football field. So that's how long the wavelength is for radio waves. Okay, the one from crest to crest on a radio wave is going to be the size of a football field. Now, as we get to smaller wavelengths going down this way, remember the frequency increases. So we go from 10 to the 6th all the way up to 10 to the 20th. Okay, so that's a lot of waves coming in per second. And those are going to be your X-rays. Anything radioactive, UV light is going to be right in here. And so the wavelengths of these are as small as a particle of your DNA. They're all smaller than bacteria. They're all smaller than one cell of your body. And even the ones, X-ray machines, have ones that are smaller than a water molecule. Okay, the other thing is too, if you look, this is energy. So as you go this way, and remember we said these are more dangerous down on this end, there's more energy from those photon or light particles that come in and hit your body. So this is why, because you have a really high energy hitting you really, really quickly, is why it's dangerous. All right, so this is what we're going to do on the next class day, and I'm going to have you guys do group presentations on types of waves. All right, so I'm going to assign you different wave types. You're going to have to tell me if it's electromagnetic or mechanical, and if it is mechanical, what kind of wave it is, if it needs a medium to go through, and if there's any cool things or any natural disasters that are associated with those types of waves. Okay, so this is just kind of a preview. We're going to do water, sound, seismic, light, shock, radio, and there'll be one more since you guys have 7 groups this year. And last year I only had 6. All right, so that's a little preview of waves. We're going to do that, and then we're going to play with Slinkies the class after that. And that'll be the last thing for Unit 5 for energy.